Today we are going to talk about intensity of magnetization and magnetic intensity. We take a Rowland ring here with a radius r and n as the number of turns per unit length, which would be equal to n upon 2 pi r as it is a circle. Inside and outside the toroid, it would be the magnetic field would be equal to 0, and the field inside it would almost be uniform magnetic field. Therefore, inside the solenoid that covers the ring, Bf in the absence of material in vacuum would be equal to mu naught Nif. We take that as equation 1. In the presence of material inside the toroid, due to bound current, Bb would be equal to mu naught Nib. Therefore, the total magnetic field would be equal to Bf plus Bb, which would be equal to mu naught Nif plus mu naught Nib, where small if and small ib would be equal to NIF and NIB respectively, which are free current per unit length and bound current per unit length. Now, let M1 be the magnetic dipole moment per unit length due to the bound current. Therefore, M1 would be equal to NIBA, which we take as equation 4. So, magnetic dipole moment due to bound current per unit volume, which is called intensity of magnetization and is denoted as M, would be equal to NIBA upon the volume. That would be equal to NIB, which would be equal to small ib is equal to bound current per unit length. Similarly, let H be the magnetic dipole moment due to the free current per unit volume, which is called magnetic intensity and is denoted as H. Experiment says that M would be directly proportional to H. Therefore, M is equal to chi m H, where chi m acts as a constant and is called the magnetic susceptibility of the given material. It also depends on temperature. So from equation 3, we can denote that B would be equal to mu naught H plus mu naught M, but where M is equal to chi m H. Therefore, mu naught H plus mu naught chi H would give this, taking mu naught and H common. Therefore, mu naught into 1 plus chi m is equal to mu, which is magnetic permeability of the given material. Therefore, dividing the magnetic permeability by mu naught would give us the relative magnetic permeability, which would be equal to 1 plus chi m, that is also denoted as Km. Now, we are going to talk about dia, para and ferromagnetism. First of all, we talk about paramagnetic material. A material is called paramagnetic when its molecules / atoms possess permanent magnetic dipole moment for paired electrons. Therefore, chi m would be greater than 0, but it would be very small. Here, if we take a paramagnetic material nail and a magnet, the anterior end of the nail would be the south pole, and the posterior end of the nail would be the north pole. Therefore, it would be attracted, but it would be a very poor attraction. The examples of these kind of materials are aluminium, sodium, calcium, O2 at standard temperature pressure, and copper chloride are paramagnetic. If we put it in a uniform magnetic field, most of the field lines would pass through the material if a slab is placed in the uniform magnetic field. The second thing that we are going to talk about is diamagnetic material. The atoms / molecules of this material do not possess permanent magnetic dipole moment due to the paired electrons. For diamagnetic material, the chi m would be smaller than 0, but it would be very small. But it wouldn't be as small as -1. Therefore, -1 is smaller than chi m is smaller than 0. If we put a diamagnetic material nail near a magnet, the anterior end of the nail would turn into the north pole, and the posterior end of the nail would turn into the south pole, thus making it repel the material. But it would still be a poor repulsion. Putting a diamagnetic material in a uniform magnetic field, most of the magnetic field lines would be repulsed, and they would not pass through the material. For example, silver, gold, copper, water and bismuth are some of the examples of diamagnetic material. The last material that we are going to talk about are ferromagnetic substances. The atoms and molecules of these kind of substances possess magnetic dipole moments, but they have a domain structure. Therefore, they have a random structure, so the dipole wouldn't be induced in a certain direction specifically. So for a ferromagnetic material, chi m would be very, very greater than 1. For example, iron, nickel, cobalt, which are usually attracted by a normal magnet. If we put an iron nail near a magnet, the anterior end will turn into the south pole, the posterior end will turn into the north pole. Thus, the attraction would be strong. If we put such a material in a uniform magnetic field, most 99.9% of the magnetic field lines would pass through the slab. Only some would not pass through the slab. So for a paramagnetic material, M would be directly proportional to B, and M would also be directly proportional to 1 upon temperature. Therefore, we can say M is directly proportional to B by T. Therefore, M is equal to C B by T, where C is known as the Curie constant. But M is equal to chi mh, as we saw that, and B is equal to mu naught h. Therefore, chi mh is equal to C mu naught h by T. So HH gets cut out, where we get chi m is equal to C mu naught by T. That implies chi m is directly proportional to 1 upon T. For diamagnetic material, chi m does not depend on temperature. For ferromagnetic material, as the temperature of a ferromagnetic material is increased, the domain structure starts getting distorted or destroyed at a certain temperature. Depending upon the material, it is totally broken up. Each and every atomic magnetic movement attains independence from one another, and the substance gets converted to a paramagnetic material. After that, chi m would be equal to C upon T minus Tc, where T is greater than Tc. The temperature at which ferromagnetic substance is converted into a paramagnetic form is called Curie temperature of that substance, which is Tc. It would be less than T.